Today we're going to talk about a new type of function that is closely related to linear functions called the absolute value function. Before we go into graphing this, we're going to talk about how do we solve absolute value equations and inequalities, and then we'll start graphing the function itself. As always, feel free to jump to a particular part of a video that you want to know about. Absolute value, by definition, is the distance of a number from 0. We indicate it with these absolute value bars. So the absolute value of 3 is 3, and the absolute value of negative 3 is 3. So in particular, on a number line, you would notice that 3 is 3 away from 0, and negative 3 is 3 away from 0. A lot of times people just remember whatever is inside the absolute value bars. That's the notation for this absolute value function. They go ahead and just make it positive. As such, if I say the absolute value of something is negative, there's no solution. So absolute value of x cannot equal a negative number, or something more complicated than x, such as 2x plus 3 or whatever. If the absolute value of something is 0 itself, then that something better just be 0. So we're going to end up with one solution. If the absolute value of something is equal to some positive number, the way that we solve that is that we break it into two mini equations, because it's either that something is the positive version of that number or that something is the negative version of that number. So in a simple case, if the absolute value of x is 3, that could mean that x is equal to positive 3 or x is equal to negative 3, because the absolute value of 3 is 3. The absolute value of negative 3 is 3. If I put something a little more complicated in there, like x plus 1, then either x plus 1 is equal to 3, and I could solve that, or x plus 1 is equal to negative 3, and I could solve that. And that's exactly how we solve these absolute value equations. So we want to get the absolute value itself by itself, so we sort of treat the absolute value symbol like it's something I need to solve for. And as long as what it's equal to is greater than 0, we set up two equations and solve. If it's exactly equal to 0, then we just have that it's equal 0, call it a day. And if it's less than 0, then we say there is no solutions. And then we also call it a day. So let's actually practice that. So for this first one, if the absolute value of something is equal to 8, then it is possible whatever that something is either equal to positive 8, or whatever that something is actually equal to negative 8. And now we have two equations to solve. So the first thing we want to do is undo adding 4 by subtracting 4 on both sides. Positive 4 minus 4 makes 0. I'm left with 6x is equal to 8 minus 4 is positive 4. Then we want to undo multiplying by 6, so we divide by 6 on both sides. 6 divided by 6 makes 1. X is equal to positive 4/6. We can simplify this fraction because 2 goes into both 4 and 6. So x is equal to positive 2/3. Or, in the other equation, we want to undo adding 4, so we subtract 4 from both sides. 6x is equal to negative 12. Then we want to undo multiplying by 6, so we divide by 6. 6 divided by 6 makes 1. Negative 12 divided by 6 makes negative 2. So x has two solutions. It's either positive 2/3 or negative 2. Notice we didn't just solve for 2/3 and then flip the sign. That's not going to work, and especially if you have anything being added or subtracted inside the absolute value sign. We do have to formally solve out two equations. For this next one, don't go on automatic pilot. If I say the absolute value of something equals negative 9, what's the problem? That's not possible. So this is no solution. There's no way the absolute value of something is negative 9. It doesn't work by definition of absolute value. This is an example where we have to do a little bit of work before we set up our two equations because the absolute value symbol is not by itself yet. So first we have to undo this subtracting 4 on the outside by adding 4 to both sides. Negative 4 plus 4 makes 0. I'm left with the absolute value of 3x minus 5 is equal to 6 plus 4 makes 10. Now I'm good to set up my two mini equations. So I have 3x minus 5 is equal to positive 10, or 3x minus 5 is equal to negative 10. Because if the absolute value of something is 10, then that something better be 10 or negative 10. Now we have two two-step equations to solve. So we undo subtracting 5 by adding 5 to both sides. Negative 5 plus 5 makes 0. I'm left with 3x is equal to 15. Then we undo multiplying by 3 by dividing by 3. So then we have x is equal to positive 5. Same deal with the other mini equation. So we undo subtracting 5 by adding 5 to both sides. We're left with 3x is equal to negative 5. Then we undo multiplying by 3 by dividing by 3. So x is equal to negative 5/3. So those are our two solutions. We either have that x is equal to positive 5 or negative 5/3. For this one, it is okay for the absolute value of something to be 0, but there is no such thing as positive 0 and negative 0. 0 has no sign. So here we just know that means negative 5 plus 10 is 0. And then we just solve our two-step equation. So we still undo addition subtraction first by subtracting 10 on both sides. So we have negative 5x is equal to negative 10. Then we undo multiplying by negative 5 by dividing by negative 5. So x is equal to positive 2. If we want to solve an absolute value inequality, then we have to think through a little bit more carefully if we're talking about an and statement or an or statement. So before we get into the math notation, let's just kind of think this through. If I say x is a variable such that its absolute value is less than 3, let's take a look at the number line. So if the absolute value of x is equal to 3, what two numbers might it be? Well, it might be negative 3 or positive 3. And I would have an open circle on both because I'm not allowed to equal. Then I want to think through here kind of each of these three regions of the number line. So is it the case that if I plug in a number more negative than negative 3, let's say negative 4, is its absolute value less than 3? No, it's not, because the absolute value of negative 4 is 4, and 4 is not less than 3. What about something in between negative and 3? Let's say 0. Is the absolute value of 0 less than 3? It is. 0 is less than 3. Absolute value of 0 is 0. We're good. And that would be true for any number in between here. Like let's say I took the absolute value of negative 1. Is its absolute value less than 3? It is. The 1 is less than 3. So numbers in between negative 3 and 3 work. And then what about something more positive than 3? Let's say 4. Is the absolute value of positive 4 less than 3? It is not. 4 is not less than 3. That doesn't work. So if I have a less than symbol, that turns into an and statement. So absolute value of x less than 3 turns into x has to be in between negative 3 and 3. And that's exactly what this math notation here says, is if I have the absolute value of something is less than a number, that's equivalent to being trapped in between the negative and the positive version of that number. Now let's think through the other way around. So let's say I had the same endpoints, but now I have the absolute value of x is bigger than 3. So if I stick that on number line, if I went through my same testing process, now when I test something more negative than negative 3, such as negative 4, is the absolute value of negative 4 bigger than 3? It is. The absolute value of negative 4 is 4. 4 is bigger than 3. We're good. What about something in between, like 0? Is the absolute value of 0 bigger than 3? It is not. 0 is not bigger than 3. That does not work this time. What about something more positive than 3, such as positive 4? Is the absolute value of positive 4 bigger than 3? Yes, it is. 4 is bigger than 3, so this end works. So if I have an absolute value of a number being bigger, absolute value of something being bigger than a number, that's equivalent to this or statement. So greater than becomes an or statement where you are more negative than the negative or more positive than the positive. Less than becomes an and statement where you're trapped in between the two. So let's take a look at this in action. So here I have less than or equal to 3. Now it's not just x by itself, but this whole thing, therefore, must be in between negative 3 and 3 because a less than or equal to becomes an and statement. And now this is a compound inequality that I can solve using my knowledge of compound inequalities. So I have one step to get x by itself. I have to undo subtracting 1 by adding 1 to all three sides. Negative 3 plus 1 gives me negative 2. Negative 1 plus 1 gives me 0. That's what I wanted. And 3 plus 1 gives me 4. So as our final solution, x is in between -2 and 4, this time inclusive because it has an or equal to sign. So in interval notation, that's from -2 to 4. Same idea here, but we want to first get the absolute value sign by itself. So what do I have to do first to get it by itself? I got to deal with this -2. Now it might be really tempting to distribute it inside the absolute value, but don't actually treat this quite like a parenthesis in that way, because that's going to mess up our inequality symbol and it just gets way more complicated than simply saying, how do I undo multiplying by -2? I can divide both sides by -2. -2 divided by -2 is 1. I'm left with the absolute value of x minus 4 is, now that I divide by negative, what do I have to do to this symbol? Flip it around, and then -6 divided by -2 gets me +3. Now this is a greater than or equal to sign, so this becomes an or statement. So it's either the case that x minus 4 is more negative, less than or equal to -3, or x minus 4 is more positive, so greater than or equal to +3. And now I solve both separately. So how do I undo subtracting 4? I add 4 to both sides. -4 plus 4 gets me 0. -3 plus 4 gives me 1. Or do the same thing here, add 4 to both sides. X is greater than or equal to 7. So in terms of our number line, we have that including the 1, x can be smaller than, or including the 7, x can be bigger than. So to translate that to interval notation, we go from -infinity to 1, bracket on the 1 because we include him, union from 7 to +infinity, bracket on the 7 because we include him. Philosophically, we always do a parenthesis on -infinity and +infinity. So we can use our knowledge of what absolute value means, which is to make what's inside the absolute value positive, in order to graph absolute value functions. Another way that you could think of absolute value functions, now that we also know how linear equations work, is that it is the equation with its same slope for whenever this thing on the inside is positive, or that you basically flip the slopes around when it's negative. This would be another way to kind of think of it as a piecewise function. But let's actually just take a look at it by graphing it by making points, and that'll make the piecewise function make a little bit more sense. So if, for example, I want to plug in -3, I just find the absolute value of -3, which is +3, and then I can go ahead and plot that. So -3, +3. Then I just keep on going. The absolute value of -2 is +2, so I have a point at -2, +2, which I almost just misplotted there. Then I want to find the absolute value of -1. Again, we're just plugging into the equation. Absolute value of -1 is +1, so I have a point at -1, +1. We can plug in 0. The absolute value of 0 is 0, so I have a point at 0, 0. Then I can plug in +1. The absolute value of +1 is +1. 1's already positive, you just keep them positive. Absolute value of +2 is 2, so I have a point at 2, 2. And the absolute value of 3 is 3, so I have a point at 3, 3. So if you notice, for all of these things that evaluated to a positive, this is just the line y equals x, and all these things were on the inside was initially negative, and then we just flipped them around. It became the line y equals -x. And that general pattern is true for absolute value equations. You'll have this 1/2 where everybody has a positive slope. You'll have this lowest point, which we will later call a vertex, which is kind of its change point. That's whenever it evaluates to 0. And then you'll have the other half where the slope is the same in absolute value, but now it's negative. So it's up 1 over 1, up 1 over 1 in one direction, up 1, left 1, up 1, left 1 in the other direction. Whenever you're plugging in something slightly spicier than just y is absolute value of x, if we have other operations going on, we want to make sure we're following the order of operations in order to evaluate what's going on this absolute value function. And in particular, you treat the absolute value sign kind of like it's a parenthesis when you're following order of operations. So if, for example, I plugged in -3, well, -3 minus -2 gets me -5. Absolute value becomes +5 plus 1 gives me 6. So now I have a point at -3, 6. Similarly here, I plug in negative 2 minus 2 plus 1. Negative 2 minus 2 gets me negative 4. Absolute value of negative 4 is positive 4. Plus 1 gets me 5. So we have a point at negative 2, comma 5. Then we plug in negative 1. The absolute value of negative 1 is 1, but of course I need to actually write the rest of the equation. So we plug in negative 1 for x, we still have a minus 2, we still have a plus 1. So absolute value of negative 1 minus 2, well, negative 1 minus 2 gets me negative 3. Absolute value becomes positive 3 plus 1 gives us 4. So we have a point at negative 1, comma 4. Absolute value of 0 minus 2 plus 1, so 0 minus 2 gets me negative 2. Make it positive, that becomes positive 2 plus 1 gives us 3. So we have a point at 0, comma 3. We keep on going, so then we have absolute value of 1 minus 2. Well, 1 minus 2 gets us negative 1. Absolute value makes it positive because it's positive 1. Plus 1 gives us 2, so we have a point at 1, comma 2. Then we have an absolute value of 2 minus 2 plus 1, so absolute value of 2 minus 2 gives us 0, plus 1 is 1. So we have a point at 2, comma 1. Then we take the absolute value of 3 minus 2 plus 1. 3 minus 2 becomes 1. Make it positive is still 1, plus 1 gives us 2. So we have a point at 3, comma 2. And if we want to keep going to see the pattern still holds, we could. So the absolute value of 4 minus 2 plus 1, so 4 minus 2 gives us 2. Make it positive is 2, plus 1 is 3. So we have a point 4, comma 3. And our total pattern looks roughly like this. So it's the same slope and absolute value in each direction, but in one half it's positive. So we go up 1, right 1, up 1, right 1, up 1, right 1. And the other half it's negative. Up 1, left 1, up 1, left 1, up 1, left 1. Of course, making the table each time, as you notice, can get kind of tedious, and it took us a while until we found this vertex again and found where the sign on the slope flipped. So there are ways in order to graph this faster. That's what we're going to go over in the next section, where we use knowledge of transformations to graph these absolute value functions. And whenever we're using knowledge of transformations, we want to keep this really basic absolute value function in mind, where it has a vertex, the lowest point at the point 0, comma 0, and then it's just going in a slope of a positive 1 in one direction and a slope of a negative 1 in the other direction. And then we're going to use transformations in order to move this graph so that whenever he moves like this, we don't have to go through the entire table each time. Although you can do the table each time if you want. There's no law against it. It just sometimes can take a while, and in particular take a while until you have found the vertex. Because if you stopped at the point, like, I don't know, here, at the point 1, comma 2, then it would start looking like a line, and you wouldn't realize it actually becomes a full V and looks like an absolute value graph instead of a linear function. So just something to keep in mind. As always, do be sure to check out your textbook if you want more examples, and be sure to ask your professor if you have questions.